Many of my fellow students went through the same experience as I did. These were some of the brightest, most talented math students around. Everybody, except for me and another student, Misha Smolyak from Kishinev, who became my roommate at the dorm, were from Moscow. Those who lived outside of Moscow could apply only if they had graduated from high school with a gold medal, which, fortunately, I had. Many of my fellow students had studied at the best Moscow schools with special math programs. Schools number 57, number 179, number 91, and number 2. Some of them went on to become professional mathematicians and now work as professors at some of the best universities in the world. Just in my class, we had some of the best mathematicians of our generation. Pasha Edinghoff, now professor at MIT, Dima Kleinbach, professor at Brandeis University, and Misha Finkelberg, professor at the Higher School of Economics in Moscow. It was a very stimulating environment. Mathematics was taught at Kirisinka at a high level, and basic courses, such as analysis, functional analysis, and linear algebra, were taught at the same level of rigor as at MGU. But courses in other areas of pure math, such as geometry and topology, were not available. Kirisinka only offered the applied mathematics program, so our education was geared toward concrete applications, particularly to oil and gas exploration and production. We had to take quite a few courses of more applied orientation: optimization, numerical analysis, probability, and statistics. There was also a large computer science component. I was glad that I had the opportunity to be exposed to these applied math courses. This taught me that there isn't really to the cafeteria, and then to the main entrance hall, elevator to the 14th floor where the auditorium was. Alexander Alexandrovich Kirillov is teaching a standard undergraduate course on representation theory along the lines of his well-known book. He also had a seminar for graduate students, which we attended as well. We got away with this thanks to Kirillov's good heart. His son Sharik, now professor at the Stony Brook University, studied at the special math school number 179 together with my classmates Dima Kleinbach and Sayoma Hawken. Needless to say, Sansanich knew about the situation with admissions at MGU. He told me many years later that there was nothing he could do about this. They wouldn't let him anywhere near the admissions committee, which was largely staffed with the Communist Party apparatchiks. So all he could do was let us sneak into his classes. Kirillov did all he could to make Kirisinka students coming to his lectures feel welcome. One of the best memories of my first college year was coming to his lively lectures and seminars. I also attended a seminar given by Alexander Rudakov, which was also a great experience. In the meantime, I was learning whatever math I could learn at Kirisinka. I was living in a dorm but coming home for the weekends, and I was still meeting Yevgeny Yevgenyevich every couple of weeks. He advised me on what books to read, and I reported to him on my progress. But I was quickly reaching the point where, to maintain my momentum, as well as the motivation for it, I would need an advisor with whom I would meet more regularly and not only learn from, but also get a problem to work on. Because I was not at Mechmat, I could not take advantage of the vast resources that it had to offer. And I was too shy to come up to someone like A.A. Kirillov and ask him to work with me individually or give me a problem to work on. I felt like an outsider. By the spring semester of 1986, my second year at Kirisinka, complacency and stagnation were beginning to set in. With all the odds stacked against me, I started to doubt that I could fulfill my dream of becoming a mathematician. Chapter 5. Threads of the Solution. I was beginning to despair when, one day, during a break in the lecture at Kirisinka, one of our most respected math professors, Alexander Nikolaevich Verchenko, approached me in the corridor. Varchenko is a former student of Vladimir Arnold, one of the leading Soviet mathematicians, and he is a world-class mathematician himself. Would you be interested in working on a math problem? He asked. Yes, of course, I said. What kind of problem? As if I would not have been happy to do just anything. There is this question that came up in my research, which I think is a good problem to give to a bright student like you. The expert on this matter is Dmitry Borisovich Fuchs. That was the name of a famous mathematician, which I had heard before. I have already spoken to him, and he has agreed to supervise a student's research on this topic. Here is his phone number. Give him a call, and he'll tell you what to do. It is quite common for experienced mathematicians like Varchenko to encounter all kinds of unsolved mathematical problems in their research. If Varchenko's problem had been closely tied to his own research program, he might have tried to solve it himself. But no mathematician does everything alone, so mathematicians often delegate some of such unsolved problems, typically the ones they consider to be simpler, to their students. Sometimes a problem might be outside of the professor's immediate interests, but he or she might nonetheless be curious about it, as was the case with my problem. That's why Varchenko enlisted Fuchs, an expert in this area, to supervise me. All in all, this was, for the most part, a typical transaction in the social workings of the mathematical world. Along with a number of other top mathematicians, trying to alleviate the effect of the discrimination against Jewish students by privately teaching young, talented kids who were denied entry to MGU. As part of those efforts, Fuchs was involved in what became known as Jewish People's University, an unofficial evening school, where he and his colleagues gave courses of lectures to students. Some of those lectures had even been held at Karasinka, although this was before my time. The school had been organized by a courageous woman, Bella Muchnik-Subotovskaya, who was its heart and soul. Unfortunately, the KGB got on the case, alarmed that there were unauthorized gatherings of Jewish people. She was eventually called to the KGB and interrogated. Soon after that interview, she was killed by a truck under suspicious circumstances, which led many people to suspect that this was in fact a cold-blooded murder. Without her at the helm, the school collapsed. I came to Karasinka 2 years after this tragic chain of events. Though the evening school did not exist anymore, there was still a small network of professional mathematicians who helped misfortunate outcasts like myself on an individual basis. They sought out promising students and gave them advice, encouragement, and in some cases, full-fledged mentoring and advising. This was the reason that Varchenko gave that problem to me, a student at Karasinka, rather than a student at Mekhmont, where, through his connections, he could have easily found a student willing to take it up. This was also why Fuchs was willing to invest his personal time to supervise me. And I am glad he did. Looking back, it is clear to me that without Fuchs' kindness and generosity, I would have never become a mathematician. I was studying math at Karasinka and sitting in at the lectures at MGU, but by itself that was not enough. In fact, it is virtually impossible for students to do their own research without someone guiding their work. Having an advisor is absolutely essential. At the time, though, all I knew was that I had in my hand the phone number of Fuchs, a renowned mathematician, and I was about to embark on a project supervised by him. This was unbelievable. I didn't know where this would end up, but I knew right away that something big had happened. That evening, having mustered all my courage, I called Fuchs from a payphone and explained who I was. "Yes, I know," said Fuchs. "I have to give you a paper to read." We met the next day. Fuchs had the physical appearance of a giant, not at all how I imagined him. He was very businesslike. "Here," he said, handing me an off-print of an article. "Try to read this, and as soon as you see a word that you don't understand, call me." I felt like he had just handed me the Holy Grail. This was an article, a dozen pages long, which he had written some years earlier, on the subject of braid groups. That evening I started reading it. The preceding 3 years of studying with Yevgeny Yevgenyevich and on my own were not spent in vain. Not only did I understand all the words in the title, I could make sense of the content as well. I decided to try to read the whole thing on my own. It was a matter of pride. I was already imagining how impressed Fuchs would be when I told him that I understood everything on my own. I had heard of the braid groups before. These are excellent examples of groups, the concept we discussed in Chapter 2. Yevgeny Yevgenyevich had introduced this concept in the context of symmetries, and so elements of the groups that we considered were symmetries of some object. For example, the circle group consisted of the symmetries of a round table, or any other round object, and the group of 4 rotations was the group of symmetries of a square table, or any other square object. And the dog barks in London. The wireless telegraph, says the physicist, is the same thing, but without a dog. After recounting the joke and waiting for the laughter to subside, even from those people in the audience who had heard it 1,000 times, Gelfand would pivot to whatever math problem was being discussed. If he thought that the solution of the problem required a radically new approach, he would comment, "What I'm trying to say is we need to do it without a dog." A frequently used device at the seminar was to appoint a kontrolny slushитель, a test listener, usually a junior member of the audience, who was supposed to repeat at regular intervals what the speaker was saying. If it was deemed that the test listener was following the lecture well, this meant that the speaker was doing a good job. Otherwise, the speaker had to slow down and explain better. Occasionally, Gelfand would even discharge a particularly incomprehensible speaker in disgrace and replace him or her with another member of the audience. Of course, Gelfand would poke fun at the test listener as well. All of this made the seminar very entertaining. Most seminars proceed at a steady pace, with people in the audience listening politely, and some perhaps dozing off, too complacent, too polite, or simply afraid to ask the speaker any questions, and perhaps learning little. There is no doubt that the uneven pace and the generally subversive character of the Gelfand seminar not only kept people awake, not an easy task given that the seminar often lasted till midnight, but stimulated them in ways that other seminars simply couldn't. Gelfand demanded a lot of his speakers. They worked hard, and so did he. Whatever one can say about Gelfand's style, people never left the seminar empty-handed. However, it seems to me that a seminar like this could only exist in a totalitarian society like the Soviet Union. People were accustomed to the kind of dictatorial powers and behavior that Gelfand displayed. He could be cruel, at times insulting to people. I don't think many would tolerate this kind of treatment in the West. But in the Soviet Union, this was not considered to be out of the ordinary, and no one protested. Another famous example like this was Lev Landau's seminar on theoretical physics. When I first started coming to the seminar, Gelfand had a young physicist, Vladimir Kazakov, present a series of talks about his work on so-called matrix models. Kazakov used methods of quantum physics in a novel way to obtain deep mathematical results that mathematicians could not obtain by more conventional methods. Gelfand had always been interested in quantum physics, and this topic had traditionally played a big role at his seminar. He was particularly impressed with Kazakov's work and was actively promoting it among mathematicians. Like many of his foresights, this proved to be golden. A few years later, this work became famous and fashionable, and it led to many important advances in both physics and math. In his lectures at the seminar, Kazakov was making an admirable effort to explain his ideas to mathematicians. Gelfand was more deferential to him than usual, allowing him to speak without interruptions longer than other speakers. While these lectures were going on, a new paper arrived by John Harrer and Don Zagier, in which they gave a beautiful solution to a very difficult combinatorial problem. Zagier has a reputation for solving seemingly intractable problems. He is also very quick. The word was that the solution of this problem took him 6 months, and he was very proud of that. At the next seminar, as Kazakov was continuing his presentation, Gelfand asked him to solve the Herer-Zagier problem using his work on the matrix models. Gelfand had sensed that Kazakov's methods could be useful for solving this kind of problem, and he was right. Kazakov was unaware of the Herer-Zagier paper, and this was the first time he heard this question. Standing at the blackboard, he thought about it for a couple of minutes to survive in this environment. Unfortunately, some speakers took these kinds of public put-downs personally, and this caused them a lot of torment. But I have to add that Gelfand always had a sharper tongue for the older, more established mathematicians, and he was much more gentle to young mathematicians, especially to students. He used to say that at this seminar he welcomed all undergraduates, talented graduate students, and only brilliant professors. He understood that in order to keep the subject moving, it was very important to prepare new generations of mathematicians, and he always surrounded himself with young talent. They kept him young as well. He was actively doing cutting-edge research till he was in his late 80s. Often, he would even invite high school students to the seminar and make them sit in the front row to make sure that they were following what was going on. Of course, these were no ordinary high school students. Many of them went on to become world-renowned mathematicians. By all accounts, Gelfand was very generous with his students, spending hours talking to them on a regular basis. Very few professors do this. It wasn't easy to be his student. He gave them a kind of tough love, and they had to cope with his various quirks and dictatorial habits. But my impression from talking to many of them is that they were all loyal to him and felt they owed him a tremendous debt. I was not Gelfand's student. I was his grand student, as both of my teachers, Fuchs and Fagin, who was not yet in my life, were at least partially Gelfand's students. Hence, I always considered myself as being part of the Gelfand mathematical school. Much later, when he and I were in the United States, Gelfand asked me directly about this, and by the look of satisfaction on his face when I said yes, I could tell how important the issue of his school and recognition of who was part of it was to him. This school, of which the seminar was the focal point, its window to the world, had an enormous impact not only on mathematics in Moscow, but around the world. Foreign mathematicians came to Moscow just to meet Gelfand and attend his seminar, and many considered it an honor to lecture there. Gelfand's fascinating and larger-than-life personality played a big role in the seminar's reputation. A few years later, he became interested in my work and asked me to speak at his seminar. I spent many hours, came to visit him at his Moscow apartment. I had just turned 21. He informed me that he considered himself the Mozart of mathematics. Most composers are remembered for particular pieces they wrote, he said. But in the case of Mozart, that's not so. It's the totality of his work that makes him a genius. He paused and continued, the same goes for my mathematical work. Putting aside some interesting questions raised by such self-assessment, I think it's actually an apt comparison. Though Gelfand did not prove any famous long-standing conjectures, such as Fermat's last theorem, the cumulative effect of his ideas on mathematics was staggering. Perhaps more importantly, Gelfand possessed an excellent taste for beautiful mathematics, as well as an astute intuition about which areas of mathematics were the most interesting and promising. He was like an oracle, who had the power to predict in which directions mathematics would move. In the subject that was becoming increasingly fractured and specialized, he was one of the last remaining Renaissance men able to bridge different areas. He epitomized the unity of mathematics. unlike most seminars which focus on one area of math. If you came to Gelfand's seminar, you could see how all these different parts fit together. That's why all of us gathered every Monday night on the 14th floor of the main MGU building and eagerly awaited the word of the master. And it was to this awe-inspiring man that Fuchs suggested I submit my first math paper. Gelfand's journal, Functional Analysis and Applications, was published in 4 slim issues a year, about 100 pages each. A pitiful amount for a journal like this, but the publisher refused to give more, so one had to cope. And it was held in extremely high regard around the world. It was translated into English, and many science libraries around the world subscribed to it. It was very difficult to get a paper published in this journal, partly because of the severe page limitations. There were, in fact, 2 types of papers that were published. Research articles, each typically 10 to 15 pages long, containing detailed proofs, and short announcements, in which only the results were stated, without proofs. The announcement could not be longer than 2 pages. In theory, such a short paper was supposed to be followed eventually by a detailed article containing all proofs, but in reality, quite often that did not happen because publishing a longer article was extremely difficult. Indeed, it was nearly impossible for a mathematician in the USSR to publish abroad. One needed to get all sorts of security clearances, which could easily take more than a year and a lot of effort. On the other hand, the number of math publications in the Soviet Union, considering the number of mathematicians there, was very small. Unfortunately, many verse writing with few details provided. What many mathematicians outside of the Soviet Union did not realize was that this was largely done by necessity, not by choice. It was this kind of short announcement that Fuchs was aiming at for my first article. Each article submitted to Functional Analysis and Applications, including short announcements, had to be screened and approved by Gelfand. If he liked it, he would then let the article go through the standard refereeing process. This meant that for my article to be considered, I had to meet Israel Moisevich in person. So before one of the first seminars of the fall semester of 1986, Fuchs introduced me to him. Gelfand shook my hand, smiled, and said, "I am pleased to meet you. I've heard about you." I was totally starstruck. I could swear that I saw a halo around Gelfand's head. Then Gelfand turned to Fuchs and asked him to show my article, which Fuchs handed to him. Gelfand started to turn the pages. There were 5 of them, which I neatly typed, slowly, with 2 fingers, on a typewriter I borrowed at Kerosinka, and then inserted formulas by hand. "Interesting," Gelfand said approvingly, and then turned to Fuchs. "But why is this important?" Fuchs started to explain something about the discriminant of polynomials of degree n with distinct roots, and how my result could be used to describe the topology of the fiber of the discriminant, and Gelfand interrupted him. "Mitya," he said, using the diminutive form of Fuchs' first name. "Do you know how many subscribers the journal has?" "No, Israel Moisevich, I don't." "More than 1,000. That was a pretty large number, given how specialized the journal was. "I cannot send you with every issue so that you would explain to each subscriber what this result is good for, now can I?" Fuchs shook his head. "This has to be written clearly in the paper, okay?" Gelfand made the point of saying all of this to Fuchs, as though it was all his fault. Then he said to both of us, "Otherwise, the paper looks good to me." With that, he smiled again at me and went to talk to someone else. Quite an exchange. Fuchs waited until Gelfand was out of the earshot and said to me, "Don't worry about this. He just wanted to impress you." And he sure did. "We'll just have to add a paragraph to this effect at the beginning of the paper, and after that, he will probably publish it." That was the best possible outcome. After adding a paragraph required by Gelfand, I officially submitted the article, and eventually it appeared in the journal. With that, my first math project was complete. I crossed my first threshold and was at the beginning of a path that would lead me into the magical world of modern math. This is the world I want to share with you. Chapter 7. The Grand Unified Theory. The solution of the first problem was my initiation into the temple of mathematics. Somewhat serendipitously, the next mathematical project I did with Fuchs brought me into the midst of the Langlands program, one of the deepest and most exciting mathematical theories to emerge in the past 50 years. I will tell you about my project later, but my goal in this book is to describe much more than my own experience. It is to give you a sense of modern math, to prove that it is really about originality, imagination, groundbreaking insights. And the Langlands program is a great example. I like to think of it as a grand unified theory of mathematics because it uncovers and brings into focus mysterious patterns shared by different areas of math, and thus points to deep, unexpected connections between them. Mathematics consists of many subfields. They often feel like different continents, with mathematicians working in those subfields speaking different languages. That's why the idea of unification, bringing together the theories coming from these diverse fields and realizing that they are all part of a single narrative, is so powerful. It's as if you suddenly realized that you could understand another language, one you had desperately tried to learn without much success. It's useful to think about mathematics as a whole, as a giant jigsaw puzzle, in which no one knows what the final image is going to look like. Solving this puzzle is a collective enterprise of thousands of people. They work in groups. Here are the algebraists, laboring over their part of the puzzle. Here are the number theorists. Here are the geometers, and so on. Each group has been able to create a small island of the big picture, but through most of the history of mathematics, it has been hard to see how these little islands will ever join up. As a result, most people work on expanding those islands of the puzzle. Every once in a while, however, someone will come who will see how to connect the islands. When this happens, important traits of the big picture emerge, and this gives a new meaning to the individual fields. This is what Robert Langlands did, but his ambition went deeper than simply joining a few islands. Instead, the Langlands program that he initiated in the late 1960s has become an attempt to find the mechanism by which we could build bridges between many islands, no matter how unrelated they may seem. Langlands is now Emeritus Professor of Mathematics at the Institute for Advanced Study in Princeton, where he occupies the office formerly held by Albert Einstein. A man of amazing talent and vision, he was born in 1936 and grew up in a small town near Vancouver. His parents had a millwork business. One of the striking things about Langlands is his fluency in many languages: English, French, German, Russian, and Turkish, even though he didn't speak any languages besides his native English before he entered college. I have had the opportunity to collaborate with Langlands closely in recent years, and we have often corresponded in Russian. At some point, he sent me the list of Russian authors that he had read in the original. The list was so extensive that it seemed he may well have read more of my native Russian literature than I have. I often wonder whether Langlands' unusual language abilities have something to do with his power to bring together different mathematical cultures. The key point of the Langlands program is the groups appear in mathematics in different guises, as groups of rotations, braid groups, and so on. We have also seen that groups were instrumental in classifying elementary particles and predicting the existence of quarks. The groups that are relevant to the Langlands program appear in the study of numbers. To explain this, we need to talk first about the numbers that we encounter in our everyday life. Each of us was born in a particular year, lives in a house that has a particular number on the street, has a phone number, a PIN to access a bank account at the ATM, and so forth. All of these numbers have something in common. Each of them is obtained by adding number 1 to itself a certain number of times. 1 plus 1 is 2. 1 plus 1 plus 1 is 3, and so on. These are called the natural numbers. We also have the number 0 and the negative numbers, -1, -2, -3. As we discussed in Chapter 5, these numbers go by the name integers. So an integer is a natural number, or number 0, or the negative of a natural number. We also encounter slightly more general numbers. A price in dollars and cents is often represented like this: $2.59, meaning $2.59. This is the same as 2 plus the fraction 59 over 100, or 59 times 1 over 100. Here, 1 over 100 means the quantity that being added to itself 100 times gives us 1. Numbers of this kind are called rational numbers, or fractions. A good example of a rational number is a quarter. Mathematically, it is represented by the fraction 1 over 4. More generally, for any two integers m and n, we can form the fraction m over n. If m and n have a common divisor, say d, that is to say, m equals dm prime and n equals dn prime, then we can cancel out d and write m prime over n prime instead of m over n. For example, 1 over 4 can also be represented as 25 over 100, and that's why Americans can say that a quarter is the same thing as 25 cents. The vast majority of the numbers we encounter in our everyday life situations are these fractions, or rational numbers. But there are also numbers that are not rational. An example is the square root of 2, which we write as follows: square root sign over 2. It is the number of whose square is equal to 2. Geometrically, the square root of 2 is the length of the hypotenuse of the right triangle with legs of length 1. It turns out we cannot represent it as m over n, where m and n are two natural numbers. However, we can approximate it by rational numbers if we write the first few digits of its decimal form: 1.4142, then 1.41421, then 1.414213, and so on. But no matter how many decimal digits we retain, this will be an approximation. There will be more digits to follow. No finite decimal number will ever do justice to the square root of 2. Since the square root of 2 is the length of the hypotenuse of the above triangle, we know that this number is out there, but it just does not fit the numerical system of rational numbers. There are many other numbers like that, such as the square root of 3 or the cubic root of 2. We need to develop a systematic way to add these numbers to the rational numbers. Think of the rational numbers as a cup of tea. We can drink it by itself, but our experience will be enhanced if we mix in sugar, milk, honey, various spices, and these are like the numbers square root of 2, square root of 3, etc. Let's try to mix in the square root of 2. This will be the equivalent of adding a cube of sugar to our cup of tea. So we drop the square root of 2 in the rationals and see what kind of numerical system we obtain. Surely we want to be able to multiply the numbers within this new numerical system. So we have to include all numbers that are products of rational numbers and the square root of 2. These have the form k over L, the square root of 2. So our numerical system must include all fractions m over n. These are the rational numbers, and all numbers of the form k over L, square root of 2. But we also want to be able to add them to each other, so we also have to include the sums m over n plus k over L, the square root of 2. The collection of all numbers of this form is already self-contained, in the sense that we can perform all the usual operations on them. addition, subtraction, multiplication, and division, and the result will also be a number of the same form. This is our cup of tea with the cube of sugar fully mixed with the tea. It turns out that this new numerical system has a hidden property that the rational numbers didn't have. This property will be our portal into the magical world of numbers. Namely, it turns out that this numerical system has symmetries. By a symmetry, I mean here a rule that assigns a new number to whatever number we begin with. In other words, a given symmetry transforms each number to another number from the same numerical system. We will say that a symmetry is a rule by which each number goes to some other number. This rule should be compatible with the operations of addition, subtraction, multiplication, and division. It is not clear yet why we should care about the symmetries of a numerical system. Please bear with me, and you will see why momentarily. Our numerical system has the identity symmetry, the rule by which every number goes to itself. This is like the rotation of a table by 0 degrees, under which every point of the table goes to itself. It turns out that our numerical system also has a non-trivial symmetry. To explain what it is, let's observe that the square root of 2 is a solution of the equation x to the power of 2 equals 2. Indeed, if we substitute the square root of 2 for x, we obtain an equality. But this equation actually has two solutions. One of them is the square root of 2, and the other is negative the square root of 2. And we have in fact added both of them to the rational numbers when we constructed our new numerical system. Switching these two solutions, we obtain a symmetry of this numerical system. To illustrate this more fully in terms of our teacup analogy, let's modify it slightly. Let's say that we drop a cube of white sugar and a cube of brown sugar in our cup and mix them with the tea. The former is like the square root of 2, and the latter is like negative the square root of 2. Clearly, exchanging them will not change the resulting cup of tea. Likewise, exchanging the square root of 2 and negative the square root of 2 will be a symmetry of our numerical system. Under this exchange, rational numbers remain unchanged. Therefore, the number of the form m over n plus k over l, the square root of 2, will go to the number m over n minus k over l, the square root of 2. In other words, in every number we simply change the sign in front of the square root of 2 and leave everything else the same. You see, our new numerical system is like a butterfly. The numbers m over n plus k over l, the square root of 2, are like the scales of a butterfly, and the symmetry of these numbers exchanging the square root of 2 and negative the square root of 2 is like the symmetry of the butterfly exchanging its wings. More generally, we can consider other equations in the variable x instead of x to the second power equals 2. For example, the cubic equation x to the power of 3 minus x plus 1 equals 0. If the solutions of such an equation are not rational numbers, as is the case for the earlier equations, then we can adjoin them to the rational numbers. We can also adjoin to the rational numbers the solutions of several such equations at once. This way, we obtain many different numerical systems, or, as mathematicians call them, number fields. The word field refers to the fact that this numerical system is closed under the operations of addition, subtraction, multiplication, and division. Just like the number field obtained by adjoining the square root of 2, general number fields possess symmetries compatible with these operations. The symmetries of a given number field can be applied one after another, composed with each other, just like symmetries of a geometric object. It is not surprising, then, that these symmetries form a group. This group is called the Galois group of the number field, in honor of the French mathematician Évariste Galois. The story of Galois is one of the most romantic and fascinating stories about mathematicians ever told. A child prodigy, he made groundbreaking discoveries very young, and then he died in a duel at the age of 20. There are different views on what was the reason for the duel, which happened on May 31, 1832. Some say there was a woman involved, and some say it was because of his political activities. Certainly, Galois was uncompromising in expressing his political views, and he managed to upset many people during his short life. It was literally on the eve of his death that, writing frantically in a candlelit room in the middle of the night, he completed his manuscript outlining his ideas about symmetries of numbers. It was, in essence, his love letter to humanity, in which he shared with us the dazzling discoveries he had made. Indeed, the symmetry groups Galois discovered, which now carry his name, are the wonders of our world, like the Egyptian pyramids or the Hanging Gardens of Babylon. The difference is that we don't have to travel to another